Welcome back to Python DSA. In this video, we are doing a complete deep dive into hash tables, the data structure that powers Python's own dict, enables O1 lookups, and shows up in almost every technical interview you'll ever face. We'll build one from scratch, understand every design decision, and cover the classic problems. Let's get into it. So what exactly is a hash table? A hash table, sometimes called a hash map, is a data structure that maps keys to values using a hash function. It's the answer to a very simple question. How do you look something up in constant time, regardless of how many items you have? Click 3 ideas make it work. First, a hash function takes a key and converts it into an integer index. Second, that index tells you which bucket, which slot in the underlying array to store the value in. Third, because of this direct addressing, lookup, insert and delete all run in O1 average time, not O log n, not ON. Constant. Click here's the punchline. Python's built-in dict is a hash table. Every time you write phone_book Alice, you are doing an O1 hash table lookup. You've been using hash tables since day 1 in Python. This video is about understanding what's actually happening under the hood. Click the diagram on the right shows the big picture. 3 keys feed into a hash function, which routes each one to a specific bucket in the array. Fast, direct, and elegant. The hash function is the heart of the whole system. It takes a key, which could be anything, a string, an integer, a tuple, and maps it to a valid array index. The formula is straightforward. Take the raw hash of the key and take it modulo the table capacity. That gives you a number between 0 and capacity -1. Click Let's trace through a concrete example with capacity 8. Alice hashes to some large integer, ending in 2, when modded by 8. Bob maps to slot 5. Carol maps to slot 0. And the integer 42? Also maps to slot 2, same slot as Alice. That's a collision, and we'll deal with it in a few slides. Click. The diagram on the right shows the pipeline. Key goes into hash, key. That integer goes through modulo capacity, and we get our index. Click 2 important, Python-specific notes. First, Python's hash is deterministic within a session, but randomized across separate runs. That's by design to prevent hash flooding attacks. Second, only immutable objects are hashable. Integers, strings, tuples, yes. Lists, and dicts, no. If you try to use a list as a dictionary key, Python will raise a type error immediately. Not all hash functions are created equal. Let's think about what separates a good one from a bad one. Click 4 desirable properties. Deterministic. The same key must always produce the same index. Uniform. Keys should spread evenly across all buckets, not cluster into a few. Fast. The hash must compute in O1 time. And avalanche. A tiny change in the key should produce a dramatically different hash, so similar keys don't land in similar buckets. Click here's a classic bad hash, a function that returns 0 for every key. Technically deterministic, but everything lands in bucket 0. Your hash table degrades to a linked list, with ON performance for every single operation. This is the degenerate worst case, and it's entirely the hash function's fault. Click a better approach, is the polynomial rolling hash. For a string, we multiply each character's ASCII value by a power of some prime. Here 31, accumulate the result, and take modulo. This is similar to how many real-world string hashing algorithms work. It's fast, it's uniform enough for practical use, and similar strings produce very different outputs. Click a diagram shows the computation for cat, c times 31 squared plus a times 31 plus t, all mod 8. Next. Even with a great hash function, collisions are mathematically unavoidable. This isn't a flaw, it's a fundamental fact. Click the reason, is the pigeonhole principle. If you have more possible keys than buckets, and you always do, since keys are practically unbounded, then at least 2 keys must share a bucket. There's no way around it. We can minimize collisions with a good hash function, but we can never eliminate them entirely. Click. So how do we handle them? 2 main strategies. Separate chaining. Each bucket holds a linked list of entries, and collisions just get appended to the list. Open addressing. All entries live directly inside the array, and when a collision occurs, we probe for the next available slot. Click the diagram shows the concrete problem. Both Alice and the integer 42 hash to bucket 2. They can't both sit in the same slot. We need a strategy. Click one more key concept. The load factor. Lambda equals n divided by capacity. Measures how full the table is. A high load factor means more collisions and longer chains. Keeping it controlled is essential to maintaining O1 performance. Separate chaining is the simpler of the 2 strategies to understand. Each bucket doesn't hold a single value. It holds a list of key value pairs. When a collision happens, we just append the new pair to that bucket's list. On lookup, we hash the key to find the bucket, then scan the list linearly for the matching key. If chains stay short, which they do with a good hash function and reasonable load factor, this scan is effectively O1. Click the code shows the structure directly. Bucket 2 contains 2 entries. Alice, 5, 5, 5, 1, 2, 3, 4, and 42, meaning both landed at index 2, both live in the same list, no conflict. Click the mermaid diagram makes the structure visual. Bucket 2 has a chain of 2 nodes. Bucket 5 has 1. All other buckets are empty. Searching for Alice, hash to 2, scan 2 entries, found. Searching for Carol, hash to some index, scan that bucket, not found, return default. Clean and predictable. Next. Open addressing takes a different approach. Every entry lives directly inside the array, no extra lists. When a collision occurs, we don't chain. We probe for the next available slot. Click 3 probing strategies. Linear probing. If slot H is taken, try H plus 1, H plus 2, H plus 3. Simple but susceptible to primary clustering. Filled slots tend to cluster together, making probes longer. Quadratic probing. Try H plus 1, H plus 4, H plus 9. Quadratic steps spread out the probe sequence and reduce clustering. Double hashing. Use a second independent hash function to compute the step size, which effectively eliminates clustering entirely. Click the diagram shows linear probing in action. Alice hashes to slot 2 and lands there. The integer 42 also hashes to slot 2, occupied, so we probe to slot 3, which is empty, and place it there. Bob hashes to slot 5 and lands directly. Click one important consequence. Deletion in open addressing is tricky. You can't just clear a slot. A subsequent lookup might stop at that now empty slot and incorrectly conclude the key doesn't exist, when really it was placed further along the probe sequence. The solution is tombstones. We'll see that in the full implementation. Before we build the full hash table, let's look at how we represent entries. Click the node class for separate chaining is minimal. Store the key, the value, and a next pointer to the next node in the chain. Click in practice though, for Python implementations. Using a linked list of node objects is overkill for small chains. Python lists are more cache-friendly for short sequences, and the append and scan operations are implemented in C, fast and simple. Click so our implementation will use list tuple per bucket. Each bucket is a Python list of key, value tuples. Manual chaining with nodes only makes sense if you're implementing in C or need a truly zero overhead structure. The callout summarizes it. Python's list is more cache-friendly than a linked list for small chains, which is exactly what we'll have with a well-maintained load factor. Let's build the skeleton of our hash table class. This establishes all the scaffolding before we implement the core operations. Click 2 class level constants, default underscore capacity of 8, our starting array size, and load underscore factor underscore threshold of 0.75. When the load factor hits 0.75, we'll automatically resize. Click constructor creates self.capacity, self.size to track the number of stored pairs, and self_buckets, a list of capacity empty lists. Each inner list is one bucket, ready to accept chained entries. Click __len, __, exposes the size via Python's built-in len. Simple wrapper around self.size. Click load underscore factor is a property, n, divided by capacity. We'll check this after every insertion to decide whether to resize. __repr, __, flattens all buckets into a single list of pairs, and formats them like a Python dictionary literal, very useful for debugging and demos. This skeleton is everything we need. Now let's add the real operations. Next. The underscore hash method is beautifully simple. Click one line. Return hash key, %self.capacity. We delegate to Python's built-in hash, then take the modulo to land in a valid bucket index. Click why use Python's built-in instead of rolling our own. 3 reasons. It handles all hashable types automatically. Integers, strings, tuples, custom objects with __hash, __. It uses cryptographic random seeding to prevent hash flooding denial of service attacks. And it's implemented in C01 for integers, O-length, for strings, but blazingly fast. Click the diagram shows the 2-step pipeline. Any hashable key goes in, hash key runs, modulo capacity runs, and out comes a valid bucket index. Click one critical constraint worth repeating. Keys must be immutable. If you try to hash a list or a dict, Python raises type error, unhashable type. String keys, integer keys, tuple keys, all fine. Mutable containers, never. Put is the core insert operation. It handles both new insertions and updates to existing keys. Click Step 1, hash the key to get the bucket index and grab that bucket list. Click Step 2, scan the bucket. If we find a matching key already in the chain, we do an in-place update, bucket equals key value, and return immediately. No size change, because we're overwriting, not adding. Click Step 3. If we exhaust the bucket without finding the key, it's genuinely new. Append the pair to the bucket and increment self.size. Click Step 4. After the insertion, check the load factor. If it's hit or exceeded 0.75, call underscore resize. This is the automatic growth mechanism that keeps performance in check. Click. The trace on the right makes it concrete. Inserting Alice. Bucket 2 is empty. Append. Size becomes 1. Inserting Bob. Bucket 5 is empty. Append. Size becomes 2. Inserting Alice again with a new value. Bucket 2 already has Alice at index 0. Overwrite in place. Size stays at 2. Clean and correct. Next, let's see the internal state of the table after inserting Alice, Bob, and the integer 42. Click. After 3 insertions into an 8-slot table, most buckets are empty. Bucket 5 holds Bob's entry alone. Bucket 2, look at this, holds 2 entries, Alice and 42. They collided at index 2 because hash Alice %8 equals hash 42 %8. Separate chaining handled it seamlessly. Both entries live in bucket 2's list, and neither one is lost. Click. The callout explains the lookup behavior. When you call get Alice, we hash to bucket 2 and scan the chain. Key Alice matches the first entry, return 5551234. When you call get 42, we hash to bucket 2, same bucket, scan the chain. Alice doesn't match, 42 does, return meaning. 2 different keys, same bucket, correct results. That's separate chaining working exactly as designed. Get retrieves a value by key, returning a default if the key isn't present. Click the logic mirrors put. Hash the key, grab that bucket, scan the chain. First match, return the value immediately. Click. If we exhaust the bucket without a match, return the default parameter. This follows the same API as Python's own dict.get, key, default. We also implement __get_item__ to support square bracket access. It reuses get, but raises a key error instead of returning a default, exactly how Python's dict behaves when you do d, missing underscore key. Click. The trace shows get Alice, hash to bucket 2, scan, first entry is Alice, match found, return 5551234. 1 comparison, in the best case. Click. The case-by-case complexity table is important. No collision, the bucket has exactly 1 entry, we return it in O1. Short chain, we do OK comparisons where k is the chain length, but k stays tiny with a good load factor. All keys collide, degenerate case, ON. That last row is why a good hash function matters. Pathological inputs can degrade O1 to ON. Next. Delete removes a key value pair from the table. It returns true if the key was found and deleted, false otherwise. Click. Same 3 steps as get. Hash the key, grab the bucket, scan the chain. On a match, call bucket.popi to remove that entry and decrement self.size. We also implement __deleteItem __ for the del ht key syntax. It delegates to delete and raises a key error if the key wasn't present. Click. The trace shows deleting Alice from bucket 2. Before, the chain has 2 entries, Alice and 42. We find Alice at index 0, call population 0, and the chain collapses to just 42, meaning size decrements. The key is gone, 42 is unaffected. Click. The callout highlights a critical distinction. In separate chaining, deletion is as simple as list.popi. The chain just gets shorter. In open addressing, you can't simply clear a slot, because a subsequent probe might stop at that empty slot too early. That's why open addressing uses tombstone markers. We'll see that in the full OA implementation. The load factor lambda is the ratio of stored entries to total capacity. It's the single most important variable governing hash table performance. A load factor near 0 means we have tons of empty buckets, wasted memory. A load factor near 1 means most buckets are occupied and chains are getting long, slow operations. The sweet spot is somewhere in between, and the standard threshold is 0.75. Python's own dict resizes at approximately 0.66. Click. When the load factor hits the threshold, we trigger _resize. The logic. Grab a reference to the old buckets, double self.capacity, create a fresh bucket array of the new size, reset self.size to 0, then reinsert every existing key value pair using the normal put path. The old bucket array gets garbage collected by Python automatically. Why reinsert rather than just reindex? Because after doubling the capacity, the hash function changes. Hash key %16 is a different number than hash key %8. Every key needs to be rehashed into its new correct bucket. Click. The diagram shows what happens to bucket 2's Alice and 42 chain after doubling from capacity 8 to 16. They get bigger moduli and may land in different buckets. Alice stays at 2, but 42 might move to slot 10. The collision is resolved. Click. The callout makes the amortized analysis explicit. Resizing is ON when it happens, but but it happens exponentially less often as the table grows. Amortized across all insertions, same analysis as Python's list, append, the cost per insert is 0.1. Let's look at the complete, consolidated implementation. Everything we've built combined into one clean class. Click lines 1 through 10. Constructor, underscore hash, load underscore factor, underscore underscore len underscore underscore, and underscore underscore contains underscore underscore. These are the helpers and existence check. Click lines 1, 2 through 17. The put method compact addition. Notice the inline hash and bucket lookup on one line. The update check, the append, the size increment, and the resize trigger, all there. Click lines 19 through 30. Get, and underscore underscore get item, underscore underscore. The sentinel pattern for underscore underscore get item, underscore underscore. We create a one-use object, as a sentinel, call get, with it, and if we get back the sentinel, we know the key was missing. This avoids any ambiguity with legitimate none values. Click lines 32 through 42. Delete, and underscore underscore delitem underscore underscore. Same shape as get, but pops the entry and decrements size on success. Click lines 44 through 54. Underscore resize. Old buckets are saved, capacity doubled, new empty buckets created, size zeroed, then all existing pairs reinserted. The old list is released. Click lines 56 through 62. Underscore underscore repr, underscore underscore, flattens all buckets into a dick-like string for clean printing. This is interview-ready code. Memorize the shape of put, get, and underscore resize. They come up directly. Next. Now let's round out the API, so our hash table behaves like a proper Python citizen. Click underscore underscore set item underscore underscore is a one-liner. Self.put key value. This is what enables ht key equals value syntax. Python calls underscore underscore set item underscore underscore behind the scenes. Click underscore underscore iter. Underscore underscore is a generator. We loop over every bucket, and for each bucket we loop over every key value pair, yielding just the key. This enables for k and ht iteration, same as Python's dict. Click keys, values, and items are thin wrappers. Keys uses list, self, which triggers underscore underscore iter, underscore underscore. Values maps each key to its value via get. Items zips them together. The API is now identical in feel to Python's built-in dict. The demo at the bottom shows it all working together. Square bracket assignments, len, del syntax, keys, and underscore underscore repr underscore underscore. Exactly what you'd expect. Next, let's see collisions happening live with a deliberately small table. We create a hash table with capacity 4, intentionally tiny, so collisions are easy to trigger. We insert 5 single-character keys, A through E. After the 5th insertion, E, the load factor exceeds 0.75 and a resize fires, doubling capacity to 8. Click inspecting the internal buckets after the resize, we can see exactly what happened. Bucket 1 has a chain of 2 entries, A1 and E5. They both hash to index 1 in the 8-slot table. All other keys landed in their own buckets. The chain for A and E is a direct, visible collision. Click, the mermaid diagram maps this perfectly. Bucket 1 has 2 nodes in its chain. Buckets 2 through 4 each have 1. The structure is exactly what we've been drawing. Buckets as an array, chains hanging off the colliding slots. Let's consolidate all the complexity numbers in one place. The core operations, put, get, delete, are all 0.1 average case. This is the whole point of a hash table. With a good hash function and a controlled load factor, chains stay short, and every operation is effectively constant. Click, the worst case for all 3 is ON, when every key hashes to the same bucket, and you end up with one giant chain. This is pathological and essentially impossible with a reasonable hash function, but it's technically possible with adversarially crafted inputs. Python guards against this with randomized hash seeds. Underscore resize is ON, it always is, but it's amortized 0.1 per insertion. Iteration is ON plus capacity. We visit every stored entry plus every empty bucket slot. That's why iteration on a very sparse table can be slower than expected. Click space is ON plus capacity. N entries, each with constant overhead, plus the capacity many bucket slots. Click the amortized cost diagram on the right, tells the full story. Individual insertions are 0.1. One resize is ON, but only once as the table fills. Then 2n more insertions are 0.1. When you average the cost across all insertions, the resize cost disappears. Same analysis as list.append. Amortized 0.1. Next. Now that you understand our implementation, let's peek at how Python's own dict does it, because it's significantly more sophisticated. Click Python's dict uses open addressing, not separate chaining. The probing uses a pseudo-random sequence derived from the hash, not linear, not quadratic, but a specific formula that avoids clustering effectively. Since CPython 3.6, dict uses a compact layout. Instead of one big array of key-value pairs, it maintains two separate arrays, an indices array, a compact array of integers pointing into the entries array, and a dense entries array storing actual hash key value triples. This layout is more cache-friendly and more memory efficient, especially for small dicts. Keys are stored with their hash value cached. That means on a lookup, Python can compare hashes first, a cheap integer comparison, before doing the more expensive key equality check. Since Python 3.7, insertion order is guaranteed. This is a consequence of the compact layout. The entries array naturally preserves insertion order. Python resizes at load factor 2/3, slightly more aggressive than our 0.75. Click the callout. Python's dict is 4 to 10 times faster than our pure Python implementation for most workloads. Always use it in production. Our implementation is for understanding, not for replacing. Where does the hash table fit in the landscape of data structures? This comparison table tells the story. For search, hash tables win with O1 average. Binary search trees and sorted structures give O log n. Arrays give On. Linked lists give On. For insert, hash tables again, O1 average. BSTs O log n. Arrays O1. Amortized at the tail but On in the middle. Linked lists O1 at the head. For delete, hash tables O1, average. BSTs O log n. Arrays On, because of shifting. Linked lists On, to find the target. Click the critical column is ordered iteration. Hash tables lose here. They offer no ordering guarantee on keys. BSTs, arrays, and linked lists all maintain some order. If you need to iterate keys in sorted order or answer range queries like all keys between 10 and 50 inches, a hash table is the wrong tool. Use a BST-based structure, like Python's sortedcontainers.sortedDict. Rule of thumb, hash table for fast key-based lookup. Sorted structure when you need ordering. These are complementary, not competing. Know when to use each. Let's implement the alternative collision strategy, open addressing with linear probing, so we can see both approaches in complete code. Click the key difference is the underscore slots array, a flat array of fixed capacity, not a list of lists. Slots contain either none for empty, a underscore deleted sentinel object for tombstones, or a key value tuple. The underscore hash method takes a probe iteration I and uses linear probing, hash key plus I, % capacity. Click put, iterates over probe positions. For each probe, if the slot is empty or a tombstone, we can place our entry there and return. If the existing entry matches our key, we overwrite it. That's an update. If we exhaust all slots without finding a place, we raise overflow error. Click get probes in the same sequence. An empty slot, none, means the key was never inserted past this point. Stop and return the default. A tombstone, underscore deleted, means something was here and deleted. Skip it, but keep probing. A matching key, return the value. Delete, probes until it finds the key, then replaces the entry with underscore deleted, the tombstone. This preserves the probe chain integrity for subsequent lookups. The tombstone mechanism is the critical subtlety of open addressing. Without it, a deletion would break the probe chain and cause incorrect key not found results for entries placed after the deleted slot. Hash tables aren't academic. They're everywhere in practical Python programming. Click Everyday Python. Dict for JSON parsing, named function arguments and configuration. Set for membership testing and deduplication. Collections.counter for frequency maps. Functools.lru underscore cache, which caches function results in a hash map keyed by arguments. Click in Algorithms. The hash table enables ON solutions to problems that would otherwise be ON squared. ToSum. Store scene numbers and check for the complement in O1. Anagram check. Character frequency map. Subarray sum. Prefix sum cache. To find target sums in one pass. Graph adjacency lists. Node. Neighbors. Is a hash table at its core. Click at the ToSum implementation is a perfect example. Without a hash table. 2 nested loops, ON squared. With a hash table. 1 loop. For each number check. If target minus n is in scene, store NON total. The hash table turns a quadratic algorithm into a linear one. Click collections.counter is essentially a frequency hash table. Feed it a word list and get counts instantly. Most underscore common, 3, returns the top 3 entries in ON log k time. 1 line of code for what would otherwise require a manual loop and dictionary. Let's run through the most common mistakes and the right way to avoid them. Click Pitfall 1, using mutable keys. Lists and dicts cannot be hashed. If you try d12 equals value, Python throws type error, unhashable type, list. Always use immutable keys, strings, integers, tuples, frozen sets. Pitfall 2, mutating a key after insertion. If you use a tuple as a key and somehow modify what it references, the hash changes. but the entry is still in the old bucket. The table is now corrupted. Don't mutate keys. Pitfall 3. Starting with a tiny initial capacity. If you know you'll be inserting 10,000 items, starting at capacity 8 means a dozen resizes. Presize with an estimate. Pitfall 4. Comparing keys with is instead of equals. Is checks object identity. Equals checks equality. In a hash table, equality is almost always what you want. Click Best Practices. Use immutable keys. Use dict.get k default instead of checking k and d and then accessing d separately. That's 2 hash lookups. Use default dict from collections to avoid manual initialize if missing boilerplate. The default dict list pattern for grouping is something you'll write hundreds of times in your career. And use counter, order dict, and other specialized dict subclasses instead of re-implementing them. Let's lock everything in. Click the core concept in one diagram. Key goes through hash key, % capacity to get a bucket index. Bucket stores the value. That's the entire idea. Everything else is engineering around that core. Click the 7 key terms: hash function, bucket, collision, chaining, open addressing, load factor, rehashing. You should be able to give a one-sentence definition of each without hesitation. Click the API reminder. HT key equals val maps to put. HT key maps to get. Del HT key maps to delete. Key in HT maps to __ contains __. Len HT gives the size. Keys, values, and items work exactly like Python's dict. Load _factor tells you how full the table is. Click the complexity recap. Put, get, and delete are all O1 average, ON worst. Rehash is ON but amortized away. Space is ON for the stored entries. Print this slide. Write it on a sticky note. Tattoo it somewhere accessible. Hash tables are in almost every interview and almost every Python program you'll write. Understanding them deeply, not just dict, is O1, but why, separates good engineers from great ones. And that's a wrap on hash tables. We went from zero, understanding what a hash function is, all the way through separate chaining, open addressing, load factors, rehashing, the full implementation, Python's dict internals, and the classic interview applications. If this was helpful, hit the like button and subscribe so you never miss a video in this Python DSA series. Drop questions in the comments, and I'll get back to you. See you in the next one.